Yes, I'm very happy to introduce our second speaker for today. That's Justin Dumouchelle. He's PhD candidate at the University of Toronto. His main interests, research interests, are in intersection of machine learning and operation research. So recently he worked a lot on learning-based algorithms. So he has another paper on neural network are using neural networks for stochastic optimization, and I think today he will only talk about the robust work we did recently. And please, Justin.
Thank you. Yeah, thank you for the introduction, and thanks everyone for attending today. So today I'm going to present Neur2RO, or Neural Two-Stage Robust Optimization. And this is joint work with Esther Julian, Janis Kurtz, and Elias Kalil. At a high level, this is essentially another machine learning for two-stage robust optimization problem, but we work within a different algorithm, so constraint and column generation. And we kind of learn and propose this algorithm in a little different style. So it's mostly a heuristic in this case, but as we'll see in the results later, we get very good solution qualities. So first, I'll start kind of with a motivating example. So Esther kind of briefly touched on this in her presentation, so I'll kind of just reiterate on it so we can all be on the same page with notation and everything. So if we think about the capital budgeting problem, our decisions are basically we're either going to invest before the uncertainty is realized or invest after the uncertainty is realized. In this case, I assume there's no loans in this problem, so we only have kind of binary decisions, but kind of our method's not really restricted to that. So just for simplicity, we only consider the case with no loans. Like before, you'll have some revenue function defined by your uncertainty, and basically, if you invest later, you'll kind of receive some reduced profit. So this eta parameter here will essentially be something less than 1, right? You might have some constraints, like obviously only investing either before or after in like a certain asset. And you'll have some budget constraints as well that are again parameterized by some function of your uncertainty. So the uncertainty itself, since we're dealing with robust optimization, is obviously going to be kind of antagonistic to our overall objective of maximizing revenue. So it's kind of going to require us to plan for the worst case. And it might be through some uncertain profit function or revenue function and some uncertain cost as well. In the capital budgeting problem, these are essentially given by deviations from some nominal demand. So essentially what you do is you project your uncertainty like demand vector to kind of the space of your decision variable. So the q dimensions to the n dimensions, and then multiply it by some nominal either revenue or nominal cost. And yeah, for more information about this specific problem, please feel free to check out the reference here. So moving on to kind of the more generic formulation for two-stage robust optimization. Basically, we can kind of imagine a problem where we have, first stage and second stage decisions, worst case uncertainty, again, being antagonistic to the optimization objective of our decisions. And we can kind of have uncertainty in almost every case, right? So in our objective constraints, right-hand side, but, in general, these problems will have, maybe 1 to 2 types of uncertainty. So just keep the general formulation in mind because I'm going to kind of, build on that as we go. The difficult part about solving this optimization problem is that, one primary challenge is solvers are kind of only, good at dealing with single level optimization problems. And two-stage robust is actually kind of like a 3-level optimization problem. So it's obviously going to require some type of, algorithmic like decision making, such as, adding rows, adding columns, or, something along those lines, right? Reformulations are also another very popular approach. In this work, we're actually going to work with constraint and column generation, which is kind of exactly what it sounds. So you start with a reduced kind of main problem. And as you go through the algorithm, you'll add more rows and more columns, or more constraints and more variables. And then you'll essentially, go until you either have an optimal solution or reach some termination criteria. So there's kind of 2 different versions of this algorithm. The first one is pretty well studied, and it's for when you have a linear programming second stage, so continuous variables in your second stage. And there's also an extension to the integer second stage, but this one is kind of a lot less studied. And it's kind of due to the difficulties of actually implementing it in practice. And I'll kind of go over just the integer second stage version of constraint and column generation, and then discuss the difficulties with it. So like I said, basically we're going to have some kind of reduced main problem that we start with. So rather than having our kind of uncertainty set over an entire polyhedral space, the key idea here is to reduce it to a finite subset of scenarios. So rather than having potentially infinite dimensional space where we're selecting our certainty from, now we're just going to select the max from a list essentially. So significantly reduces the problem and relaxes it quite a bit. But the nice thing about this is it basically allows us to get this single level reformulation. So here, essentially, because we have a finite number of scenarios, you can essentially create an objective and a scenario constraint for each scenario, along with decision variables for all of those, and then just take the worst of all of those when you're actually solving the optimization problem. So that's how you, I guess, solve the main problem for a finite set of scenarios. And now you have to ask yourself, okay, well, once I do that, how do I get more constraints and more columns? Well, that's where the kind of adversarial problem, or AP, as we'll kind of refer to it in the rest of this talk, comes into play. And essentially, when you solve the main problem, you'll get some candidate solution, X star, which I've kind of highlighted in blue here. So this is now going to be a fixed value in our optimization problem, and we only need to solve that innermost kind of max min problem. So that's basically the two types of, I guess, like mathematical optimization problems that you'll need to solve for constraint and column generation. So to kind of put this all together, it's a pretty simple algorithm, but basically you'll start with some finite set of scenarios, and then you'll compute a first stage decision from the main problem based on that finite set of scenarios. So you'll get some candidate solution, X star. From here, you'll then compute the worst case scenario using the adversarial problem. So for that particular X star, what's the worst case scenario? From here, you can check optimality or whatever termination criteria you may have, and you'll either need to continue the algorithm, adding that scenario to your set of scenarios and redoing steps 1 to 3, or you'll be finished by reaching some termination criteria and terminate. So that's kind of just the high level of constraint and column generation. And there's kind of two aspects of this that make it very difficult to implement in practice. So we'll first start talking about the main problem. And essentially here, what we have is, if you look at this reformulation, there's one challenging part that's going to become very difficult to solve as the main problem increases in constraint and columns. And that is essentially, for the second stage variables, we need to have a copy of them for every scenario, right? So if you have, let's say, a bunch of binary or integer variables in your second stage, and you're copying them multiple times, you have 10 scenarios or something, it's going to be very, very difficult to solve this problem as the number of scenarios increases. So that's kind of what makes solving the main problem difficult. In terms of the adversarial problem, in kind of the most general form where you have something like constraint and objective uncertainty, it actually results in kind of a bi-level optimization problem with integer follower decisions, which is kind of another like classically very hard optimization to solve. And the difficulty here is that both of these are going to need to be solved kind of routinely. So that kind of is why constraint and column generation is very difficult to implement in practice. You're solving both of these very hard mathematical optimization problems, and you need to do it kind of iteratively and expand them as your algorithm proceeds. So now I'm going to kind of present the main contributions of our work and I guess our methodology as a whole. And the key idea here is we first want to train a machine learning model that can estimate the second stage value function, or basically that innermost objective of the optimization problem. So I'll show that in a second in more detail. But we then want to take that trained predictive model and use that to formulate an easier to solve main and adversarial problem. So to kind of address the second stage value function, we basically want to formulate our prediction task as follows. So on the left-hand side of this inequality, I basically have a neural network parameterized by theta, and it takes as input our first stage decision and scenario. And then on the right-hand side, I have the objective for a fixed scenario uncertainty, right? So all I need to do is solve this minimization problem over y, simple like, single stage optimization problem, and take the objective as my label. So that's really what we're trying to do with prediction in this case. In terms of formulating easy to solve approximations, basically what we're going to rely on is kind of the work that uses kind of representing or formulating trained machine learning models in integer programming models. So for example, if you have a neural network with ReLU activations, which are piecewise linear, you can represent those with variables and constraints in a MIP, and then use the prediction and optimize over your predictive model in that sense. But this also extends to kind of various predictive models. So like something like random forests or decision trees, there's also ways of encoding those into optimization problems as well. But in this work, we kind of leverage neural networks, and you'll kind of see why as I kind of go through the presentation. So with that, I'm going to move on to actually formulating the main and adversarial problems using a trained neural network. So we're going to assume that we've trained some neural network to predict the second stage optimization or second stage optimal value function, and then I'm going to use that in practice to actually formulate my main and adversarial approximations. So for the main problem, if you look at our objective here of the like minimization problem, it's our first plus second stage. So essentially what we can do is say, okay, well, I'm just going to have some free variable eta that's just going to be greater than or equal to this for all of the scenarios, right? So I'll need to embed a neural network for each scenario. So that might not be, the easiest thing to optimize over, but this gives kind of a very simple, way of looking at the problem. I just need to solve this, simple like minimization problem, and then I'll get some first stage decision from there, and I can then use that within constraint and column generation. So assuming I solved my main problem, get some candidate solution X star, the adversarial problem now is only optimizing over the like maximizing over the output of the neural network for a fixed first stage decision. So you basically fix your first stage decision, and then you'll have your uncertainty, which is what you're optimizing over, and you're optimizing it to maximize the output of the neural network. Again, you can solve this with like MIP formulations, but there are even like kind of faster first order methods that you can use to approximate this very well, much faster than actually trying to solve the like MIP itself. So this is kind of the two ways of formulating the main and adversarial problem. And now I'm going to go into one contribution we make in this work, which is actually formulating a little bit smarter of a version of the main problem. So if we look at this version of the main problem, it looks fine as is. And, if our predictive model is, 100% accurate, then there's really nothing to worry about, right? But in practice, you're really never going to get a predictive model that's completely accurate. And this formulation, heavily relies on the quality of our predictive model, right? We're essentially doing regression everywhere. And we're not leveraging kind of any of the original like information about the main problem or the two-stage robust optimization problem. We're only really leveraging the regression of our neural network. The idea here is to propose an improvement on this, where we actually use the network more as a classifier to identify the worst case scenario, and then we combine that with the actual kind of coefficients of the problem. So what do I mean by that? Well, essentially here in this last constraint, we'll have our neural network. We'll have all the copies of it embedded, and rather than using just the like regressor output, all we're going to do is take the argmax over kind of the worst case. So now we get the scenario that is corresponding to the worst case, and then we'll use that scenario and propagate that information into the actual like constraint and objective coefficients, right? So this basically allows us to use that true coefficients of those true coefficients of the problem, and use our neural network to kind of be used as a classifier for identifying scenarios. And we compare both approaches in the paper, and the second one is kind of better across the board in almost every case. So pretty strong empirical argument for it. So with that kind of out of the way, I'm going to now kind of dive into what we mean by using a neural network to predict. And I'm going to start with kind of just the most basic way of using a neural network here. So basically here, we have some value network. So I'll assume that this is just some feed-forward neural network with some number of layers, right? So what I'm going to do is I'm going to take my first stage decisions, X, and my uncertainty, Psi, and I'm going to concatenate those together and use my neural network to predict on that concatenated vector, right? And I'm going to predict my second stage value function here. So this is fine, and it may work well for if you have relatively small first stage decisions or scenario spaces. But if you have a really large first stage input variable, say X is something like 100 dimensions, you're going to need to scale up the size of your value network in order to predict well on that, right? So if you have very small X, you can probably have a small value network and do well. But if X and your uncertainty are very large, then you're going to need to proportionally increase the size of the value network. And why does this create an issue? Well, if we go back to our main problem formulation, we're going to need to represent that kind of feed-forward neural network phi in our optimization problem, right? So it's going to require basically a large number of binary variables and big M constraints to represent those piecewise activation functions in our neural network. So if we have a large network that we're embedding multiple times, it's basically going to require a huge number of variables that we're adding to the problem, which really isn't going to get us that much efficiency over kind of the standard constraint and column generation, right? So that's where we kind of propose a new architecture to handle this type of problem. So here, The main idea is basically we want to keep the input into the value network into a very small dimension so that we can keep the dimension of the value network very small. So what do I mean by that is essentially we want to embed both our first stage decisions and our scenarios into small dimensional representations, and then use those rather than just using our inputs directly into the value network. So this can all be trained kind of end to end with gradient descent. So this is just kind of a standard like deep learning architecture. So very easy to, I guess, train. It doesn't really create any complexity there. But now I'll kind of discuss why we get some savings and optimization. So I'm first going to start by discussing the main problem. So when you give me a main problem, I'll essentially have some finite set of scenarios that I know ahead of time, right? So the scenario embedding network, we can actually pre-compute all of the kind of vectors here, which are the scenario embeddings, right? So in my main problem, I've kind of represented that here in the blue. So this is essentially just going to be constants in our optimization problem. And we don't really have to worry about optimizing in that sense. For the first stage embedding network, all we have to do in this case is embed this a single time. And then these variables here are basically going to act as intermediate variables in our optimization model. So we can get away with only embedding that first stage value network a single time. Even if it has to be larger to accommodate, say, a larger first stage decision, it's only going to occur once in our optimization problem. If we look at our value function or our value network here, we're going to need to embed this, number of scenario times. However, since we can keep our inputs very small, we can get away with using, a much smaller value network in this case. So the main part that we're going to be, complicating our main problem with, adding a new value network in each iteration, we can keep this very light. I think in our case, we were able to keep this to something like 8 hidden units. So we only need 8 binary variables and 8 big M constraints. Every time we add, every time we increase the number of scenarios in our main problem, whereas like these problems in like classical CCG would have something like 80 or 160 binary variables. So relatively big savings in that context. In terms of the adversarial problem, it's a similar story, but in this case, we're only worried about optimizing over a single scenario, and we don't have multiple scenarios. So in this case, our first stage decision could be pre-computed and essentially fixed in the adversarial problem, denoted in kind of blue here. And then our scenario embedding network can be kind of formulated once in the adversarial problem, as well as our value network. So then you just have to solve this optimization problem instead. Okay, so up to this point, we've only dealt with kind of looking at a single fixed problem, right? So I've assumed that both the dimension, like let's say the capital budgeting problem, like the number of assets is like fixed, and I've assumed that the like cost and like budget parameters are fixed as well, right? Which is kind of a limitation. So we have to do all this data collection and train a model for a single instance. In this work, we propose a kind of generalization of that. And the main idea here is to actually encode our decisions with their corresponding information, right? So basically, you'll have your first stage decision, which is whether to invest in your asset 1 or not, and then you'll have like relevant constraint and objective information, which in this case would just be your nominal cost and your nominal revenue, essentially. So you just concatenate all of that together and then pass that through a feed-forward neural network, and you essentially do that for all of your different items. And if you want to generalize kind of across, different sizes of or a different number of assets, for example, then what you need to do is apply some type of aggregation. So you can use something like the sum or the mean, which is a relatively common approach in deep learning. And this is known as like set-based neural networks, right? Very similar to graph-based as well, if you're more familiar with that. So the main idea here is to basically just leverage problem information so that we can now train a model that works across different instances rather than just focusing on a model that works on a single instance. In terms of kind of an overall like algorithmic setup, essentially we just add a few steps to the standard constraint and column generation. So here we essentially have first a data collection phase where we sample instances, decisions, and scenarios, and then solve the corresponding second stage optimization problems. And then we have a second step, which is to train a neural network to predict the second stage value function. From here, we kind of go into the standard CCG steps with our revised formulations. So here we compute the first stage decision, then get the worst case scenario, check optimality, and we're either going to continue or terminate. And the nice thing about this is that if you're concerned with optimizing over a family of instances, let's say you have problems that you need to solve routinely. So that last model was particularly useful. Then you have this offline training phase, which you're going to do, kind of once from, let's say, historical data or from some distribution of, data that you think is going to be realistic in your day-to-day setting. And then every time you give me a new instance, I can just deploy that same trained model without having to, worry about these two kind of initial steps. So basically, offline training phase and then a deployment phase afterward. We do have some theoretical results. So basically, if our first stage decision set is finite, so if you have something like binary or bounded integer first stage decisions, then we know that this algorithm will terminate in a finite number of iterations. And we're kind of actively looking to extend both this proof, but also some ideas around like how far away is our solution quality based on the quality of the predictor and things like that. So experimental setup, I'll kind of give a very brief overview. So we look at two-stage robust optimization problems. The first is the knapsack problem, and the second is the capital budgeting problem, both with kind of their respective baselines, so branch and price and k-adaptability. All optimization is done for a 3-hour time limit. And in terms of just some simple machine learning details, we basically train a single machine learning model for each problem class. We have a data collection and training phase that is 2 hours or less than 2 hours for both problems. So we have two models. We take, less than 4 hours to train both of them. And we do no hyperparameter tuning at all. But that would only really kind of increase the performance. So now we'll move on to results. So I'll start with the knapsack results. So there's essentially 4 different classes of instances that kind of vary in their correlation type, with uncorrelated being kind of the easiest instances and strongly correlated being the hardest instances. So on the left here, what I essentially have is a kind of box plot of the relative error. So if we look at just, for example, this 20 item instance, I have 18 different instances here. And then this is just a box plot of the relative error, which is the gap to the best solution between the two algorithms. So in this case, we can see, branch and price, it's a very small instance and it's uncorrelated. So branch and price is able to solve this very quickly. If we look kind of across the board, you can see, well, branch and price actually gets, optimal solutions on all of these instances. So this gives us a chance to at least compare our algorithm to kind of ground truth in this case, where we can see we're getting like something like, on average, probably 1 to 2% gap from a optimal solution. When we move to kind of the more challenging instances is kind of when we start to see actual performance benefits. So if we look at these weakly correlated instances, you can see here that, for something below 50 items, maybe it doesn't really make sense to use our method. But as we go to, as we go to 60, 70, and 80 items, we actually start to do better, especially at 80 items. We're now getting, better solution quality. And we can see on the right here that branch and price is now taking something like 3 hours, whereas we're taking something like 30 to 130 seconds, typically for these larger instances. So we get, very good solutions very quickly. If we move to the harder instances, so adding more correlation, you can essentially see that as soon as we get to 50 items or more, now we're getting kind of better distributions of solution quality at huge reductions in computing time. So essentially, the baseline is kind of almost timing out at 3 hours for every instance as soon as you get to 50 items, whereas we're taking something like 10 to 30 seconds to solve these. So we're getting very good solutions, if not better, in much less time, which is kind of a very strong computational result. For capital budgeting instances, we compare to k-adaptability with k equals to 2, 5, and 10. So the kind of best known solution is computed with respect to those now. So all 4 algorithms. And we can see here that we have a pretty similar story. So especially when you go to something like 40 or 50 items, that's when the distributions that we achieve with our method are kind of much more favorable over k-adaptability. In terms of running times, again, we get roughly 1 order of magnitude speed up, and we're kind of actively looking to improve that with other techniques. I mentioned first order techniques, so we think we can get even faster solutions in this case. Yeah, and with that, I'll kind of summarize. So basically, we have a recipe for two-stage robust optimization, and it kind of relies on learning to predict the optimal second stage value function and embedding those predictive models into an approximate version of CCG. We got very good solution quality, state of the art on kind of larger instances with orders of magnitude speedup, and we're generic to various kind of two-stage robust optimization problems. If you're interested in the code, you can scan the QR code on the bottom right here and the paper on the just next to it on the left. And in terms of future work, we're kind of actively exploring a few directions. The first is more challenging two-stage robust optimization problems, specifically ones with kind of difficult constraint uncertainty, as well as algorithmic enhancements and theoretical guarantees, as I kind of alluded to. So yeah, with that, I'll conclude, and I'm happy to answer any questions. And If you want to email me, my email is listed at the top right there. Thank you.